So let's have a look at this problem. It's researchers investigating the age of different types of drug abusers, and we see we've encoded them as those in group A, B, and C. And we're just going to imagine that we want to discover whether there's a difference in the mean age between these three groups. But in question number 1, we need to create dummy variables. So we're going to say that let's take group A, those encoded as group A, to be the reference group, and from this data set of the first 9 subjects, we need to create dummy variables. So let's have a look at that. So let's say this first individual was in group A for 2, B, A, C, B, C, A, and B. Now, if the reference group is A, we're only going to create dummy variables for group B and C, because what we just want to know absence and presence. And the way mathematically to show absence is to multiply something by 0, and then that something that, in inverted commas, would disappear. If you multiply something by 1, you don't change it, so that something remains present. And that's the whole idea here. So if we look at this first individual who's in group A, group B, well, that's not present for them, so we put a 0. C is not present for that, and we put a 0. And we can still identify, if we only looked at these two dummy variables, we could still identify this person as belonging to group A, because 0, 0 would uniquely identify them as being in group A. So the same is going to go for the second individual. And then we're going to have, well, for this third individual, B is actually present, so we're going to put a 1, C is not. And so for any row, remember, there can only be 1, 1, because no one can be in both, have the presence of being both in group B and C. Now, this person would then be 0, 0. This person would be 0, 1. 1 would be present for that. This one would be a 1, 0. We would have a 0, 1. We would have a 0, 0, and a 1, 0. So we have dummy variables. By dummy, we mean we've added new data, new columns to our spreadsheet, if you want to think of this as a spreadsheet. And this is what we're going to use. We don't put the reference group because that information is not necessary. If you think about it, there's 3 different values that we can write here across these two. It's 0, 0, 1, 0, and 0, 1. So we still have 3 unique entries, and we don't require A. So let's look at question number 2. If we look at question number 2, let's have a look at it here. It says, test their claim that the mean age of these drug abusers is not the same for all 3 types at the 5% level of significance, given the information in the table below. The table's coming, where we have a total of 150 subjects. I think what was not printed out here is that there's exactly 50 in each group, so let's just remember that. We get the means for everyone in group A, everyone in group B, and everyone in group C. That's the mean age, if our random variable is age then. And we also see the sum of squares total, the sum of squares due to the regression, and the sum of squares due to the residual or the error term. We get the numerator degrees of freedom and the denominator degrees of freedom. So this is what the table looks like. And so we see 150, so let's just take it that it should be a 50 in each group. We see a mean age of 27.14 for group A, 29.76 years for group B, and 29.78 years for group C. We see the sum of squares due to sum of squares total, sum of squares due to the regression, sum of squares due to the error. We know if we add these two, we should get the sum of squares total, which it seems to be. We get the numerator degrees of freedom. That's going to be the number of parameters in our model minus 1. And the degrees of freedom in the denominator, well, that's going to be the sample size minus the number of parameters in our model, and that's going to be 147. So this information is given to us, but we'll see in a model that these two, especially these two, are in fact so. So that's our question, and we need to determine that. So let's go through our steps, to test whether these means are different from each other. That's going to be a hypothesis test. So for hypothesis test, let's put step number 1. Step number 1 is going to say, well, what are the population parameters that we're interested in? This is 150 simulated data from 150 individuals, but they're taken from a larger population. So we're going to say, well, we are interested in the population parameters. Let's say mu A, mu B, and mu C, where mu is a population mean. So this is going to be the mean age of everyone in the population So let's just keep it simple. Everyone in the population, I'm going to say in group A, but remember, by that we do mean, by group A we don't mean just the little 150 people that we're talking about, as everyone taking, taking that illicit substance. And so this is going to be for everyone taking substance B and everyone in the population taking substance C, and that's going to be the mean populations there. So in step number 2, let's write our null hypothesis. Our null hypothesis, we can say that mu1, or mu A in our instance, equals mu B in the population mu C. So no matter what illicit drug the members of this population take, their mean ages are the same across all three of them. That would be equivalent to saying that beta sub 1 equals beta sub 2 in a model equals 0. And our alternative hypothesis then would be at least one population mean is different from the others, and we would write that here we'd write either beta sub 1 is not equal to 0 or beta sub 2 is not equal to 0. Why can I state these two as equivalent? Remember, we're going to get a model, and our model is going to say something like this, that if we get the average, this mean estimated age of some individual, that is going to be beta sub 0 hat plus beta sub 1 hat times whether they are in group B, and remember that can only take a value of 0 or 1, plus beta sub 2 hat, and whether they are in group C or not. So if we put a 0, 0, that's what we're saying, beta sub 1 and beta sub 2 are both 0, those two values disappear, and I don't want to put my hand on it because things wet. All I'm left with is beta sub 0 hat, which means irrespective of the group, we're always going to have the same value for the estimated, the mean estimated age. And that's always just going to be that value, so that all three are the same. So you're going to see how either writing your null hypothesis and alternative hypothesis in this form, or whether you write it in this form, it's completely the same thing. So in step number 3, we were told to use a level of significance of 0.05. Let's do step number 4. So what we're going to use is one-way ANOVA. One-way analysis of variance. Now we're going to use an F-test, in other words. And if we wanted to state the main assumptions, remember we always want independence of our random samples in each group. We really want a normal distribution of ages within each group in the population. We want equal variances across these values. We're just going to assume for, in this course that those assumptions hold, so we can carry on with our calculations. So let's take a look at this F statistic that we have to calculate. I'm going to write it here. The F statistic for us is going to be, we're just using the fact that this is just a linear model, that ANOVA comparing more than 3 means that is just a linear model. So we'll use what we've learned in multiple linear regression and say that this is going to be the SSR. Let's have our ruler. We're going to divide that by the numerator degrees of freedom. And we're going to divide all of this by the SSE. We're going to divide that by the denominator degrees of freedom. And remember, this is described by the F distribution under these 2 degrees of freedom. Those are the parameters for the F distribution, and that is under the null hypothesis. And we do know that nu sub 1 equals k minus 1, and nu sub 2 equals n minus k. And why can I say k equals 3? Well, if I look back at my model, it's going to be beta sub 0, beta sub 1, beta sub 2, hat, all estimates. And so there are 3 parameters to this model, and 3 minus 1 is 2, and 150 minus 3 is 147. So we know if we take step number 5 and we calculate this, we're going to say that F, our F distribution, so let's have a look at those values. Let's put them here. So we have our SSR is 230.573. divided by k minus 1, which is going to give us 2. And that's divided by the SSE. We see the SSE there is 4425.72. And we divide it by n minus k, which we have there is 147. So if you plug that in your calculator, hopefully you get the same as me. I get about 3.83. 3.83, that is our F statistic. And so in step number 6, we've got to compare this to a critical value. So if we're looking at a F critical value, that would be F, let's write that, F critical. Now you have to use software, or usually in the exam, I'm just going to give you those. That is going to be 3.06. Remember, that's for our F distribution. We want to go 95% of the area under the curve across because we're using an alpha value of 0.05. And that specific curve is going to be created by the fact that we have the parameters 2 and 147. So if we look at our F statistic, our F is larger than the critical value. 3.83 is larger than 3.06. And hence, what we do is we reject the null hypothesis and we accept the null hypothesis, we accept the alternative hypothesis. So in step number 7, when we have to write a test conclusion, we're going to write, I'm going to say there's enough evidence in the data at the 5% level of significance to show that at least one population mean is different from the other. So that means all the population means are not equal. And once we've done this, we can go on to question number 3, only because we've rejected the null hypothesis of this F test. And so question number 3 is if the null hypothesis is rejected, which we've done, perform post-hoc analysis to determine which groups have differing means from each other. So we have to do a couple of t-tests. We just do pairwise comparisons. Remember, t-test compares two means to each other. So let's have a look at question number 3. And so for question number 3 is, let's just first decide, what pairwise comparisons can we do? And we can obviously compare group A to group B. We can compare group A to group C. And we can compare group B to group C. So there are 3 pairwise comparisons that we can make. And it should be clear from an equation that we have. And that is Q minus 1, and we divide that by 2, where Q is the number of these groups that we have. So we have 3 groups. 3 minus 1 is 2. 3 times 2 is 6. 6 divided by 2 is 3. We have 3 pairwise comparisons. So we've got to do 3. We've got to do 3 of these t-tests. So let's have a look at them. Let's do step number 1. We're just going to state the population parameters. So for this first one, we're going to have mu A and mu B. I'm not going to write that out. That is the mean age in the population of people who fall in group A. In other words, are using that specific substance. And for the second one, we're going to have mu A and mu C, and we're going to have mu B and mu C. By A, B, and C, as I say, those are just encodings for the population who take that specific illicit drug. So if we go to, let's go to another page. If we look at step 2, if we look at those null and alternative hypotheses, let's put H sub 0 and H sub 1 there. This one is going to have that mu, and this is going to be A minus mu B equals 0. And here we're going to have mu A minus mu B is not equal to 0. They're just different from each other to tell the alternative hypothesis. Here we'll have mu A minus mu C is equal to 0. Or in other words, mu A and mu C are equal to each other. Or mu A minus mu C is not equal to 0. And the third t-test will have mu B minus mu C equals 0. And we'll have mu B minus mu C is not equal to 0. So 3 t-tests that we have to do. For step number 3, we've got to choose an alpha value. Now we're going to use the Bonferroni correction here, and we're going to say that this adjusted alpha, which we might write alpha with a little line there, we're going to say that that is alpha, which we had before, and we're going to divide that by the number of pairwise comparisons that we have. And we have 3 pairwise comparisons to do. And so the alpha value is going to be 0.0167. That is now going to be our level of significance, and this is called the Bonferroni correction. So we're correcting for compounding these type 1 error, the type 1 errors that we can make. So step number 4, what test are we going to use? Well, we're going to do pairwise t-test. So we're going to do pairwise t-tests. And the assumptions for those tests are the same as we've just had for the f-test. Let's just look at what we have here. We're going to have a t-statistic. And that t-statistic is going to be mu. I'm going to say I minus mu j, where I is not equal to j, meaning I've got A and B, A and C, and B and C. I don't have A and A. These two cannot be the same. So we look at those differences in those two means. Now, I've got to actually say that under the null hypothesis, we say that is 0. So what we actually want here is xi minus xj minus those two. Forgive me for that little minus there. This is 0. So it's the difference in those two sample means. And we're going to divide that by the square root of the SSE. Then there's many algebraically equivalent ways to write this. And we're going to do n minus k. And then we're going to have 1 over n sub I plus 1 over n sub j, where that is the sample size of my two groups that I'm comparing at the moment. And that is going to be under the null hypothesis, under h sub 0. And we also know the degrees of freedom for this t distribution, because that is going to be described by t distribution on certain degrees of freedom under the null hypothesis. That's going to be n minus k as well. So for everyone. So just to be clear there, it's the sample mean minus the sample mean minus these two, but under the null hypothesis, which is what we're doing, that is 0 anyway. So it's just the difference between the two sample means that is described by the t distribution under certain degrees of freedom, and that's going to be n minus k, or 150 minus 3. So in step number 5, we can actually calculate that. So we're going to do that for all of them. So here we're going to have t equals, let's bring back our solution set. And so for A and B, that's going to be 27.14 minus what B was, 29.76. That's going to be divided by the square root. And we have the SSE, that's 4425.72 divided by 150 minus 3, and that's going to be 1 over 50 plus 1 over 50. We have 50 in each group, we decided. Okay, so that's going to be our first t-statistic. The second one's going to be this, calculated in the same way. I'm not going to write it out, but that'll be b minus c, so it's going to be, or a minus c I should say, so that's going to be 27.14 minus 29.78 divided by the same standard error. And then for the final one, B and C, it's going to be 29.76 minus 29.78 divided by this same standard error. And so what I want to do here is just write these. Let's write T, A, and B. Now check on your calculator if you get the same thing. I get negative 2.39 for the T, that's A and C. I get negative 2 let's say negative, equals negative 2 I get negative 2.41, and BC, I get negative 0.02. So in step number 6, if we look at the critical T value, that's going to be 2.42, that's plus or minus 2.42. This is a two-tailed alternative hypothesis. And we can see none of them, now remember this was on an alpha value of 0.016, so you've got to be careful there. 2.42 are critical values on the negative side, on the positive side, and we can see none of these three values. We fail to reject H sub 0, and here we also fail to reject And here we also failed to reject. In all three cases, we failed to reject. That is not in the region of rejection. That is almost there, but it's not, and that's not there. So how can that be? Because and when we write our test conclusion, we did an F-test, we did our analysis of variance, and that showed that, well, at least one of the means is not equal to the others. But now we come to the pairwise test and we see, well, none of them do we show that there's a difference between the two groups. And that really comes from the fact that we do have this adjusted alpha value. And what is happening is we're making it very difficult for ourselves. The critical values are going to move way out because our alpha value is much smaller. So we are decreasing the type 1 error rate here. And it's more difficult to show a difference between two means, and hence none of these do we. And so our final result will be, we've got to write a test conclusion for each one of these. So remember, we do have to have a step 7. We do have to have a step 7 for each of these, and in all three we're going to write that there is not enough evidence in the data at the 5% level of significance to show that there is a difference in the mean age between people in group A and people in group B, and by those I mean in the population taking illicit drug A and illicit drug B, and you're going to say the same for A and C, and you're going to say the same for B and C. So all three conclusions that you would have to write there. And do not be surprised if you do find a real-life situation where your analysis of variance, your F-test rejected the null hypothesis, but when you do the pairwise analysis, the post-hoc analysis, you do not find. Mostly you will, but do not ever be surprised in real data analysis if you do then fail to reject each of your post-hoc tests.